All right, guys. So the lecture that we're going to start through today is the last lecture for Unit 1. So this really deals with our different types of homeostasis and the feedback loops or the feedback mechanisms that help us to maintain that. All right. So homeostasis, by definition, is just the maintenance of a stable internal environment. Okay. The big hallmark here for homeostasis is that it is a dynamic equilibrium. All right. So it's not something that is static, it's constantly changing. And we have to be able to maintain that homeostasis to be able to not only um, ensure normal body function or normal function within the body, but also sustain life. All right. Most of the time, when somebody has some sort of a disturbance in that homeostasis, we call that a homeostatic imbalance. So every chapter that we go through, starting with our tissue, well, maybe not starting with our tissue chapter, but definitely with the integumentary chapter, will be some sort of disease process that results from an imbalance in the system. Okay, so let's go and take a little bit of a look at the basic parts of the homeostatic mechanism and take a look at kind of how we maintain that. All right, so the basic parts you can see here in the graph, but there are three basic parts that are a little bit more important than the rest of them. So the first part is the receptor, all right? Second part here is the control center, and the third and final part here is the effector. So the whole process here is working, and they use this kind of teeter-totter example because if something goes out of balance, we're looking at it either going out of balance in a value that is too high or going out of balance in a value that is too low. All right, body temperature is probably our best example that we usually use when we talk about homeostasis, because the average kind of set position here for homeostasis for body temperature is really close to 98.6 degrees. Now, I think I've talked about this before. You're going to see people that have temperatures a little bit above 98.6 degrees and a little bit below 98.6 degrees. But whatever their set value is this homeostatic value here at the middle. So what'll happen here is when it becomes out of balance, there is some sort of stimulus that changes that. So if it's body temperature, if it's 98.6 degrees is what this balance point is, if it gets to 99 or 100, now we have a stimulus. That stimulus is going to be picked up by the receptor. In the case of our body temperature, our receptor is our hypothalamus. Our hypothalamus is in our brainstem. So that receptor in our brainstem picks up that our core temperature is above that 98.6 degrees. Right? It sends that information via what's called an afferent pathway. An afferent pathway sends information to the control center. Okay, you're going to notice that there are two pathways here, afferent, and I'm going to talk about efferent here in just a second. So my way of remembering this is afferent starts with an A. I think at the control center. All right, so that's going to take information towards or at. All right, it's going towards the control center. The control center then is the one that keeps the set value. All right, so the control center says, I want 98.6 degrees, but I just got information from the receptor that says we're 100. All right, so the control center says, well, we're 100. We need to decrease body temperature. So it's going to send its information, or essentially its fix, along an efferent pathway. Efferent starts with an E. This is away or exiting the control center. Again, at exit. All right, so this is exiting the control center and going towards what's called an effector. All right, and it's going to cause the response that the control center wanted to try to bring our body temperature back down to the set value. So in the case of body temperature, if we're above 100, if we're above 98.6 degrees, this response is going to be for us to sweat. So our sweat glands will open up, start to produce fluid. Right? Our blood vessels near the surface of our skin will dilate, causing more blood to rush to the surface of our skin to try to cool us. Right? So because we're trying to use our skin essentially like a radiator at this point. And a lot of our other processes within our body will actually start to slow down. Our metabolism will slow down. Metabolism is going to increase body temperature. We don't want that at this point. Right? And we'll continue to do that. Those couple things, sweating, vasodilation, and repressed metabolism until that set point coming back to the control center says 98.6 degrees. Right? If that doesn't happen, we just continue that process until it gets back to there. Same thing happens if we go the other way. If we're 98.6 degrees is what we're looking for, and we're 95 degrees, we need to increase body temperature. So now that stimulus will be picked up by the receptor that says we're 95. The control center says, whoa, wait a minute, we're not supposed to be 95, we're supposed to be 98.6 degrees. We're going to send a signal now to vasoconstrict. We're going to clamp those blood vessels down near the surface of our skin. This is why when you walk outside and it's cold, your fingertips get cold and your nose gets cold really quickly, all right, because those parts of our body are seen as expendable. So because we're vasoconstricting in those areas. And then one of the other things that will happen is we will increase muscle contraction, which causes friction, which increases body temperature, and we will also increase metabolism. So we'll start to burn food faster to try to warm ourselves up. All right. Again, this whole thing is working and trying to get it back to that set point. Okay. So this just kind of talks back through those basic processes again. So this whole thing is a communication through both neural as well as hormonal. So it's between the nervous system and our hormones a lot of time that try to help maintain homeostasis for us. All right, here's your three parts: receptor, control center, effector. All right, receptor, again, is going to respond to the changes in the environment. It's looking for this stimulus. Okay, it's looking for something that tells it that something is not the way it should be. All right, it's going to send its information to the control center. The control center then is the portion of the system that determines those set points. All right. If it's body temperature, it's 98.6 degrees. If it's blood pressure, it's 110/80. If it's blood sugar should be around 100. So all those things are held by the control center. The control center is going to analyze this information that's coming from the receptor, all right, and determine if there's some sort of action that needs to happen, or determine essentially what's called the appropriate response, right? If our body temperature is 98.6 degrees and the information coming from the receptor, the control center tells it that, it's not going to do anything. We don't need to do anything. Our set point is already there. But if it's out of whack, we need to be able to have some sort of response. That then is carried out again by the effector, right? And the effector is what's going to provide the means for the response. Most often, these effectors are going to be some sort of gland or some sort of organ in the body that's going to produce a hormone for us. And that hormone will hopefully give us the effect, okay? But most of our systems, real quick, are all done this way. They've got a receptor, a control center, and then finally an effector for this portion, okay? There are two types of feedback mechanisms, all right? One is negative and the other is positive. Negative is the most common, okay? Almost every system we have in our body is a negative feedback system, right? We have very few, in fact, only 2 or 3 that are actually positive systems, okay? The negative feedback system is designed to essentially just shut off the original stimulus. So it receives the stimulus, but it just ignores that stimulus until the information coming back to the control center says we've gone back to homeostasis. So in essence, your body doesn't care that your body temperature is 101 or 104. All right, it's going to do the same things to try to get your body temperature back to that 98.6 degrees. All right, again, the same way if it goes the other way. So it doesn't care how far below 98.6 degrees it is. It's just going to continue to try to produce that 98.6 degrees. Most often people refer to negative feedback systems working very similar to like the thermostat in your house. Okay, so your thermostat in your house is your control center. It holds the set value. So you set the dial on your thermostat to say 68 degrees. Okay. In the summer, if the temperature falls above 68 degrees, the control center is going to tell the HVAC system in the house to turn on and start producing cold air, to turn your air conditioning on. All right. It will continue producing air conditioning until the control center reads 68 degrees again, and then it will finally turn the air conditioning off. Same thing happens in the winter. If 68 degrees is what we're looking for and the temperature falls below that, the control center will now tell the furnace to turn on and produce heat until we get back to that 68 degrees. All right. Negative feedback systems shut things off and just bring us back to baseline. They don't do anything else besides that. They're just trying to get us back to that set point that we're looking for. Okay. Positive feedback systems, on the other hand, increase that original stimulus. That's the big difference. Negative systems shut off that original stimulus. Positive feedback systems increase it, meaning they're trying to push that stimulus further along to other systems. All right. So the example that you're seeing here is childbirth. Our only real two examples of this process are blood clotting and childbirth. Once childbirth has started, as long as we're far enough along in the pregnancy, we want that process to continue, not stop. All right. The reason for that is because the baby actually releases a hormone when it no longer can get enough nutrients from the mother. All right. It's reached a point in development where it can survive on its own. It's also reached a point in development where the mother can no longer produce enough nutrients via that contact between the placenta and the umbilical cord to feed this growing baby. That baby will release its own hormone, essentially triggering childbirth, and then the mother's body will take that triggering of childbirth and continue to push it further along, so that way that process continues. If this were a negative feedback system, the baby would initiate childbirth, the mother's body would stop it. The baby would initiate it, the mother's body would stop it. And honestly, that's sometimes the reason why we see some issues during childbirth, is because the mother's body is trying to put it back to normal. All right. And sometimes we have to give drugs or other type of interventions to continue this process, because the mother's body can't push this fast enough to get childbirth to happen quick enough. Okay. Blood clotting is the same way. Again, we have a clot or a cut in the body or some sort of damage that causes a clot. All right. If that clot were allowed to stay there, that clot could open back up and we could bleed again. So the basic premise here is that we want to get the clot to start, and then the clot will actually release its own hormones to cause healing to take place. All right. Those basic systems have to be in place. Otherwise, we would just stop bleeding and then it would quit. Right. We would never form a full repair of this place where this clot has kind of lodged itself. Okay. So big takeaways from this lecture are the stages, or kind of the parts of the controls of the homeostatic mechanism. All right. So you've got your receptor, control center, effector. All right. I would remember those three parts, and I would also remember them in order. Okay. I would remember your afferent pathway, your efferent pathway. Afferent is going at the central nervous system. Efferent is going away or exiting the central nervous system. Okay. I would know what each one of those parts does. So I would know what the receptor does. I would know what the control center does, and I would know what the effector does. Okay. I would also know the difference between positive and negative feedback. I would know which one is more common. Okay. Those are some of the questions that probably will show up on the quiz coming up on Friday. Okay. All right. We're going to go ahead and stop there.